Okay, so this presentation is quite closely related to the previous talk in that we are also looking into the dispersion of smoke haze from biomass burning or wildfires in Southeast Asia. But in our analysis, we are using a Lagrangian dispersion model and run this model on wildfire emission rates that are estimated from active fire detection, so from the measurement of fire radiative power. So this work is done as a collaboration between the Meteorological Service Singapore and the Met Office of the United Kingdom, and this collaboration was initiated after the very severe smoke haze event of last year, which you already heard a lot about actually in the last talk. So yeah, you already know that this event was quite unusual regarding its severity and timing. And a recent study actually showed that most of the area that was burned was on peatland that had already been deforested in previous years. So it was actually cropland and not forest that was burning. And interestingly, during this event, we had the highest fire radiative power ever detected with the MODIS instruments. So in order to be better able to predict future impacts of biomass burning on air pollution levels in Singapore, MSS and the Met Office have been working together to set up a quantitative transboundary haze forecast system for Singapore. And in the run-up to this, we have analyzed some recent haze events in the region using this emission products from active fire detection. And in the next slides, I'm going to show you some examples of those validation studies and discuss the quantitative bias we have detected in our simulation and a way to overcome this by introducing a real-time bias correction mechanism in our operational haze forecast. So first, let's have a look at the main model components. So at the core of the model system lies the Lagrangian dispersion model NAME that is operated and developed at the Met Office. And with NAME, we are modeling the distribution of pollutants in the atmosphere in a Lagrangian stochastic framework by tracking an ensemble of particles along their trajectories in space and time. And we are running NAME for these studies on three-dimensional meteorological fields from the Met Office's unified model in its global configuration. And in order to represent the wildfire emission sources in NAME, we use two different data sets, both of which are derived from the measurement, satellite-based measurement of fire radiative power. So on the one hand, we have the global fire assimilation system, GFOS version 1.2, which is operationally produced at ECMWF. And on the other hand, we have a product that is computed or compiled at MSS, which is done in a quite similar fashion as the GFOS algorithm, but MSS use much more up-to-date and better resolved land cover maps that particularly have a better representation of the peatland in the area. However, a disadvantage of this dataset is that currently MSS is not using the full sophisticated GFAS algorithms. For example, there's no correction for partial cloud cover at the moment. Okay, let's have a look at some of the results from the validation study, starting with last year's event. You have already heard that we had very high fire hotspots in this Riau province in central Sumatra. And we have data available from an air quality measurement network in Singapore, and we simulate this, the haze event with NAME now. In NAME, we only include the wildfire emissions in our source terms, so we don't have any other anthropogenic or natural PM10 emissions, so we are constantly lacking a background level of pollution in our modeling, so you need to take this into account. So what you can see here are daily and hourly average PM10 concentration observed in Singapore in this measurement network, together with the NAME MSS and NAME GFAS simulation results. And we have added a constant background concentration of 30 microgram per cubic meters. And we needed to scale the NAME GFAS simulation results by a factor of 2 in order to match the concentration levels we see in the field. But the unscaled MSS values actually matched those peak concentrations quite well. So we see that particularly during the peak period of the event, we capture the magnitudes quite well after applying those scaling factors and also the short-term variability. But overall, the width of the peak in name MSS is more narrow than in name GFAS, which probably hints at an underrepresentation of the fire activity and fire persistence in this data set. So in both data sets, we see that we don't quite capture the exact timing of the onset of the event, and we also do not capture this elongated tail at the end. So let's have a look at some of those periods in more detail, starting with the onset around the 15th of June. So here you can see concentration averages of concentration plumes of PM10 from name GFAS and name MSS, together with the corresponding emission levels on these fire hotspots, and the meteorological situation as predicted by the unified model. So during the onset of the event, we had very weak southerly winds, which initially pushed the plume further northwards before it entered this region of higher wind speeds, westerly winds, and gets transported to the Malayan Peninsula. So initially, in both simulations, we had Singapore just sitting at the edge of the plume center line, and that's probably the cause of these discrepancies here. When we move over to the peak period, we still have very dry weather conditions over central Sumatra, and the winds now have picked up quite a bit, and the plume or the emissions are getting directly transported across the Malacca Strait to the Malayan Peninsula, and Singapore is directly in the plume now. The dry weather conditions persisted, and so did the high fire activity, even after the concentrations have already started to decrease in Singapore. And again, this is due to the fact that we had a change in the wind speed. So now again we have more southerly winds, very weak winds, pushing the plume further north. And again, Singapore is just at the edge of the plume, of the high concentration area of the plume. At the end of the event, around the 25th of June, we had an increase in convective activity in the area, and these rainfall rates helped to subdue most of the fires, which is also visible in those reduced emission rates. And again, we have still very weak winds, and the plumes in the simulation tend to, stay in place. So a possible factor that contributed to the discrepancies we see might be that due to the increased cloud cover, the fire radiative power estimated or measured with MODIS is not as accurate as before. And furthermore, low intensity or smoldering fires are likely to remain in the region, and those FRP values are likely to be below the detection threshold in MODIS. We also had a look at two other haze events in the region. This time we're having a look at the Mekong sub-region. And so here we have a periodic recurrence of very bad air pollution, or very high air pollution, particularly in March and April. And we have data available from 4 measurement sites in northern Thailand, and simulated the haze events in 2013 and 2014. So here you can see results of those simulations. Again, we have used both emission data sets. We have added a background concentration, and this time we determined via regression analysis correction factors between 5 and 6 for the emission inventories. But we have a very good qualitative match of some of these traces. And after applying these correction factors, we are well within a factor of 2 of the observations with our simulations. The same is true for this year's event, which was quite similar to what happened last year. So this is really something that's occurring periodically in this region. So from those past analyses, we have seen that in general, we are able, based on those active fire detection products, we are able to simulate those haze events quite well qualitatively with this dispersion model, but that we need to apply some bias correction in order to arrive at the right quantitative concentration levels. And we've also seen that those correction factors seem to vary depending on the region and probably also the seasonality, so it cannot be expected that those values are applicable to any future event. So for an operational forecast system, which we set up for Singapore, we need to have a more flexible bias correction scheme. And for this forecast system, we are now using an additive bias that we apply to our raw model forecast. And this additive bias is the median residual between past observations and past simulations over the 24 hours prior to the forecast issue time. So what you can see here is again a time series of this haze event in June. And this time, this red line is the name GFAS run with using this bias correction scheme. And compared to the factor of 2 scaling that we have used previously from the regression analysis, we see that we are able to increase the simulation accuracy, particularly for name MSS. So we have been running the operational system during this year's haze season by using this bias correction technique, and here you can see an example of such a forecast. So what you can see here in this gray shaded area is the hindcast period in which we use or we simulate the hindcast for the previous day using the actual sources information from the satellite products, and then compute the bias between our raw simulation and the measurements in Singapore, and apply the median bias to the future forecast. And for the forecast, we currently persist the sources information that we had available at the end of this hindcast period. Okay, so I'd like to wrap things up now by having a quick look at what was going on in terms of haze conditions in Singapore this year. So compared to last year's event, which was a much more mild season, we had some haze activity in March, and again this was due to fires in the Riau province in Sumatra, which were actually equally intense as what was going on last year in June, but this time due to the prevailing wind situation, Singapore was not as heavily affected. There were some minor episodes of haze in September and October, this time mainly from fires in southern Kalimantan and southern Sumatra. And in the next part of the project, we will have a look at those events and see how our operational system has performed. And it is also planned to switch to the use of limited area NWP models to drive the name dispersion model, because they have a much better resolution and might pick up some important meteorological features that we are not able to pick up with the global model at the moment. MSS will continue to work on improving the source terms based on those high-resolution land cover maps, and it is also planned to explore the potential to use information from geostationary satellites, for example, in order to include a daily cycle of fire activity and to have a more clever way in order to persist our sources for the future evolution of the fires that we need for the forecast. And in a more long-term perspective, we are also planning to integrate those wildfire sources in a full air quality model for Singapore. Okay, thank you.
We'll have time for questions. Please.
Can you just elaborate on the plan and how to incorporate the Lagrangian model?
Sorry?
Can you just elaborate on the plans for
The plume rise? Okay, so, well, the Lagrangian model, because it runs on meteorological data, it already takes into account convective effects. But the plume rise in this sense is more targeted at the emission product. So what we have from GFAS at the moment is emission rates plus some kind of information about the injection height of the plume, which is also related to the fire intensity. And at the moment, with the MSS data set, we are using a constant injection height of 800 meters. But from the GFAS product, we saw that this can vary quite significantly between, well, a few decameters up to 1 kilometer or even higher. So a future plan is to also move to include those information in the MSS data.
Do you just carry a single smoke
Yes. So so in the Lagrangian model, we have those particles, which are not actually particles, but some mathematical formulation of a particle. And yes, we do account for wet and dry deposition. So based on the precipitation fields that we get from the NWP model, we model the deposition of those particles to the ground due to rain out or washout, so in cloud scavenging and below cloud scavenging. So this is all included.
The particle itself doesn't age.
Well, yes, it has a time component, and it can I'm not sure if this is, so there's no chemistry attached, so we don't have any chemistry for those particles.